Welcome to part 3 of the Interferometer series. In this part, we will focus on a new mechanical design and an improved optical layout for the device. So let's start by taking a look at the previous implementation and some of its flaws. First, I would like to briefly discuss the topic of alignment. The interferometer we are building has 6 degrees of freedom that need to be adjusted. 2 angles to make the laser beam parallel to the direction of motion. This is easily done by providing tip and tilt adjustment of the entire device. Next, 2 translations of the corner cube reflector to align the reference beam to the measurement beam. This will be done by a suitable mount, which still needs to be developed. And finally, 2 inner degrees of freedom to align the corner cube reflector with the beam of the stabilization arm. For this, the old design uses screws to tip and tilt the entire optical assembly within the device. I see this mechanism as the first flaw of the old design. It is not very easy to adjust and requires more space than I would prefer. Another mechanical issue is the collimator lens holder. Even though the lens is internally spring-loaded, it easily shifts around, which invalidates the alignment of other components. Additionally, I would have preferred the stabilization arm length to be longer in order to obtain a more accurate signal when the laser wavelength drifts. The fourth, and perhaps biggest problem with the old design, is related to unwanted tertiary reflections within the beam splitter. When we look at the beam path presented in an earlier video, we can see how the light from the measurement arm passes through the beam splitter and reaches detector 2. Unfortunately, a double reflection within the beam splitter causes some light to reach the corner cube reflector of the stabilization arm and then detector 1. This leads to crosstalk from the measurement arm into the stabilization arm, which contaminates the signal for wavelength stabilization. This can also be observed experimentally. Notice how the intensity at the right spot slightly changes when adjusting the length of the measurement arm. However, when switching sides by moving the corner cube reflector into the second beam path, the artifacts disappear. Looking at this new optical layout, it becomes clear why this simple solution works. The unwanted reflection is now directed out the edge of the beam splitter, where it is easily absorbed. In this section, an enhanced design is presented that addresses the previously mentioned issues and incorporates the corrected optical path shown here. To make the video more practical, I will discuss the specific changes made during the build process of an actual prototype. A key change is the selection of the base material. As shown on the screen, the old design uses a carbon fiber reinforced plastic bar. It provides high stiffness and very low thermal expansion, but only along the direction of the fibers. However, some parts of the beam propagate perpendicular to the fibers, which is not ideal. Therefore, the plan is to switch to a more homogeneous material that still maintains the low thermal expansion properties. The perfect choice would be specialized ultra-low expansion glasses or materials such as ZeroDur. Unfortunately, these are not so easy to come by and are rather expensive. An affordable alternative that can be purchased used or even found in scrap is glass ceramic cooktops. Even broken ones will do. I will explore this material in more depth in the future, but for now, I will use a standard glass sheet as a substitute for the prototype. Here you can see the old mount for the corner cube reflectors. It worked well in principle, but it's too bulky for the new design. Additionally, during some tests, I noticed that the protective paint on the large flat surfaces is quite delicate and flakes off easily. This makes it unsuitable as a surface for mounting the reflector. In contrast, the glass beneath the curved surfaces on the perimeter has a rough texture, which allows the paint to adhere much better. Therefore, we will use this area as the mounting surface, utilizing the following small mild steel part. Mild steel is chosen because it has a relatively low coefficient of thermal expansion compared to other commonly available and machinable materials. Additionally, the part has a very small interface surface where it is glued to the base. This interface must absorb differences in thermal expansion since the base plate will have a CT close to 0. Here you can see how a 3D printed template is used to glue the reflector to the mount. Notice how the rotation of the reflector is aligned. Make sure you make no mistake during this process, since the mount cannot be removed from the reflector without stripping the paint. With the corner cube reflector assembly complete, we can focus on the next part, the adjustable laser mount. It will enable precise tip tilt adjustment of the beam while also securely holding the collimator lens. The laser mount consists of two parts, the base, which is machined from mild carbon steel with relatively low thermal expansion, and the diode holder, machined from brass. The diode holder is attached to the base using 4 screws. The center screw pulls the two parts together, while the 3 grub screws are used to adjust the angle. I might make a separate video on the machining of the parts, but for now, here are the finished components. The construction files for all parts, including the machining paths, will be available on the GitHub repository. I also changed over to free CAD to make everything more accessible for others. With all the new parts completed, the next step is to mount them to the base plate using glue. To easily position each part correctly, a 3D printed template card is used. The 3 protrusions on the bottom help locate the template on the base by referencing 2 edges. The first component to be mounted is the fixed part of the laser holder. Note that for this prototype I'm using cyanoacrylate glue, also known as super glue, which holds surprisingly well. However, for the final build, I would recommend using a 2-component epoxy like JB Weld. For the beam splitter, I used a small right-angle prism to position it perpendicular to the base plate, but other tools can be used as well. A tiny amount of water is used to temporarily attach the beam splitter. Next, the corner cube reflectors are attached. Make sure to orient them correctly, as the small steel part is slightly asymmetric. Failing to do so will position the reflector too high. I just want to briefly mention that the small steel part holding the reflector allows for the assembly to be removed from the base plate. This would not be possible if the reflector were glued directly to the base, as the reflective silver coating would peel off. After all parts are mounted, the template can be removed carefully. Note that the second corner cube reflector is missing here, as I didn't have it at the time. Next, the laser diode holder can be attached to the base and aligned to a neutral position. I previously mentioned that a drawback of the old design was the relatively short length of the stabilization arm. In the new design, this issue is improved by adding length to the device and folding the beam path with a mirror, effectively doubling the distance. The mirror I am using is a dichroic mirror from an old DLP projector. It has very high reflectivity for green light, which can be tested by placing it in the beam and checking if any light passes through. Dichroic mirrors for the correct wavelength can also be ordered online without too much difficulty. Again, a 3D printed part will help with proper alignment before gluing the mirror to the base. As you can see here, a piece of a microscope slide is permanently glued to the 3D print. I will again use a small amount of water to temporarily attach the mirror to the jig. For the following steps, it is important to select and focus on the correct one of the two beams. The jig offers 2 degrees of freedom for adjustment, vertical adjustment, using the rear screw, and horizontal adjustment by sliding the jig along the base. You can now see how the mirror is adjusted correctly. Remember, this is just a rough alignment, and any errors can be compensated for later using the laser mount. However, it's important the components are roughly in the correct position. When good alignment is achieved, the mirror can be glued to the base permanently. After the glue has cured, the jig can be removed. This concludes the mounting of the optical components. The last topic I want to cover in this video is the case. The case not only protects the optical components from the environment, but also shields the beam path from air currents. These can disturb the stabilization arm measurements by causing changes in the refractive index of the air. In the presented design, the case will also incorporate the photodiode readout electronic board. The readout PCB will be an intrinsic part of the case and provides the top cover. Since the board is not yet designed, I will use a 3D printed placeholder, which can be identified in the upcoming clips by its white color. The frame of the case will be 3D printed. Since both the PCB and the frame are made of materials with large coefficients of thermal expansion, special care must be taken when designing the mounting solution. The design must also prevent any bending moments from being transferred to the base plate, as this could alter the reference beam lengths. A kinematic coupling is an excellent choice for these requirements. The type used here features 6-point plane contacts to precisely constrain all 6 degrees of freedom of the case. The contacts are magnetically preloaded to keep everything securely in place. This principle is implemented by embedding 6 small cylindrical magnets into the case walls. Each pair of magnets rests on a bearing ball glued to the base. The magnets not only provide preload, but also the hard metal contact surfaces for the spheres. During the installation process, the correct polarity should be respected to produce strong field lines through the steel balls. This step concludes today's build. Of course, the interferometer is not finished yet, and there are still many aspects to cover. Nevertheless, we can take a moment to assess our progress and observe some fringes emerging from our little prototype. Here, interference within the stabilization arm is shown. Of course, once the detectors are in place, the beam will remain completely inside the device. For now, however, keeping the beams unobstructed aids in inspecting and adjusting the interference signal. Expanding the beam with a lens lets us see the pattern more clearly. By adjusting the laser mount, the measurement beam of the stabilization arm can be aligned precisely to the reference beam. To demonstrate this, the device is temporarily misaligned. Fog makes the beam paths visible. Note that some of the beams will be blocked by the detectors in future.